This is lesson 5.2 on logarithmic functions and their graphs. So please turn to page 373, I think, in your textbook, and we will get this one started. Okay, so I would strongly encourage all of you to have this relationship from logarithmic form to exponential form on a handy card that you can keep in front of you. A lot of our properties and a lot of our solutions are going to be found by simply being able to transition from log form to exponential form and then applying any of our properties that we've been talking about and will continue to talk about in this section and future sections. So you guys on your own need to be able to identify that y equals log base a of x is the same thing as x equal a to the y power. So again, I urge you to put this on a card that can just stay in front of you no matter where you're at through chapter 5. Okay, so checkpoint number 1 on page 373 has us evaluating each logarithm at the indicated value. Now, I'm going to stress that in these, we're supposed to be able to evaluate these algebraically, which means that you should not be punching these in and coming up with a calculator value alone. It requires some steps. I'm going to try something a little bit different than what I did in class, and maybe it's going to help those of you or a couple of you who I may have not had on board with me. And I'm just going to stick that value of x in from the very beginning. So rewriting this problem, f of x is the same as y. You guys know that. But I want to evaluate log base 6 at x is equal to 1. All right, so I'm going ahead at the very beginning step here and putting the 1 in place. All right, obviously this is written in log form. Okay, exponential form has x equals a to the y, if you recall. So I'm just going to take the elements from my log form and I'm simply going to rearrange them. So now x will equal a to the y power. Okay. Now, if 1 is equal to 6 to the y power, I'm trying to figure out what the value of my function is or what my value of y is that's going to have this happen. You guys all know that the 0 power is equal to 1. So in this particular problem, that power, or my y, must be the number 0. Let's take a look at example B. Okay, so y is equal to log base 5 of 1 over 125. Okay, so I am again going to apply my, my card, and I'm going to rewrite this in exponential form. So my x value is that 1 over 125. And that is equal to a, which in this problem is a 5, to the y power. All right, so now this is kind of similar to what we were looking at in section 1. I want to be able to apply one of my properties. In fact, I'm shooting for turning this into a one-to-one property application. And I see 5s in this problem on both sides. Okay, currently 1 over 125 is 1 over 5 to the third power. So that's partway there. I don't want that 5 to the third power in the denominator, though. I want it to be in the numerator or on top. So if I change my power of 3 to a negative 3, I'll get that. So 5 to the negative 3 is equal to 5 to the y. Now you can use your one-to-one property and get that negative 3 is equal to y. Okay. I didn't leave myself a whole lot of room for C at the bottom there, so I'm going to kind of move over to the right-hand side of my slide here to do that one. I'm going to do it in blue so it keeps it separate from A and B. So currently, I have, okay, this is part C, y is equal to log base 10 of 10,000. Rewrite. So x, which is 10,000, is equal to 10, which is a, to the y power. So this one's not so bad. I think you guys all recognize that 10,000 is 10 to the fourth power. And then our one-to-one property tells us that 4 is equal to y. We practiced a little bit of this in class, but again, back to page 374. Make sure that you know how to use the log key and you can key in those values and get them to match your book. Let's do a couple of the checkpoint ones at the bottom of the page. Checkpoint number 2, letter A, was x is equal to 275. So if in my calculator I punch in log of 275 and hit enter, I should end up, and you should end up seeing the value 2.439333 roughly. Okay, now if you try this one, you are going to get an error message. Because again, taking something to a power or to a power will never result in an x value of -1/2. Okay. All right, the properties of logs. Again, this table came from page 374 in your textbook. We talked about them today in class, and I'm hoping a few of you are starting to see the similarities here. There's always a way to use our rewriting and solving algebraically to prove these properties, so it's not absolutely essential for you to memorize them. It will be a time saver if you remember things like log base a of 1 is equal to 0 and log base a of a is equal to 1. But you can do your rewrite and end up proving it to yourself anyway. Okay. Let's put some of these to work. All right, so log base 9 of 9. Again, if you remember it from the property, you can get the answer right off. But if we were to simply look at this as y is equal to log base 9 of 9 and do our rewriting, x is equal to a to the y power is how it would be rewritten. And this is the same as 9 to the first power on the left-hand side there, and then my one-to-one property gives me my solution. Okay, the value of 20 to the log of 20, log base 20 to the 3 power. This one is written in exponential form already. I think you guys can all see that 20 is raised to a power. So this one is currently sitting in this arrangement. All right, so here is a, and this whole thing is your power of y. So if I'm going to rewrite this in the log form, remember that one looks like this. The y part is that whole exponent, log 20 of 3. The a in this problem, like we identified, was a 20, and then we have our x. So both left and right side have log base 20. So our one-to-one property says that for this one, my value of x is going to be a 3. Okay, letter C, log base root 3 of 1. That one is in log form. So currently we have this. So in rewriting it, I'm going to have x is equal to a to that y power. So again, I have something raised to a power equaling 1. The only thing that's going to make that happen is a power of 0. So that y, or that power for this problem, has to be a 0. Root 3 to the 0 power is 1. Y is equal to 0. All right, checkpoint number 4 on page 375 in your book. It says use the one-to-one property. Okay, so we should be looking for the fact that we have it, or we're going to have to do some rewriting to get it. Nicely enough in this example, both left and right side of this equation have that log base of 5 staring at us. So we are ready to transition right into using that one-to-one property. So being the logs match, the values of x also need to match. So solving. So I need the roots of 9, plus and minus 3. Now the graphs of our log functions, you can generate XY tables to help you with these. Your graphing calculator has the capability of helping you with these. But let's just take a look at these with that XY table, because you guys know me well. That's kind of how I do things. If we have f of x equals 8 to the x, okay, and I generate a list of values here. If I go with, I'm just going to go with a few here. My values of y that come out are going to be 8 to the negative 2 power would be 1 over 64. 8 to the negative 1 is 1 over 8. The 0 power of anything is equal to 1. And then the first power and the second power would be as such. Okay, so then graphing this, at -2, I'm barely going to want to lift off the axis here, because -1 isn't much higher. 0, 1, 1, 8, oops, 1, 8. I almost did that backwards. So you can see that we've got an asymptote here that we're going to hug. And then it's going to take off very rapidly as our x values increase. All right, now letter B, our g of x equation, is written in log form. So the first thing I'm going to do is I'm going to kind of switch that around. I want that in exponential form so I can make my t-table for that one. So x is equal to a to the y power. Now, whether or not on your own you would compare this to the y equals 8 to the x function that we started with, you'll notice in these two the only difference is that the x and the y have been swapped. That means that these two must be inverse functions of each other. Okay, remember when the domain and the range switch, that comes from switching your x's and y's in your functions. So you can go ahead and generate another t-table if you want, but the fact that I've recognized that these two are inverses of each other, I'm just going to flop my columns around. And I have values that I can graph. I'll do this one in blue, I think. So barely off the 0 mark and then down at -2. Oops, wrong side. Pen didn't line up real well there. Hang on. Well, that's a little better. Then at -1, I'm at, oops, not at -1. At 1/8, I'm at -1. Okay, so still not very far off it. A little bit better. 1, 0 is a point. 8, 1 is a point. And that's all that's going to fit. So I can see I'm going to hug this one. There's my asymptote, and then it's going to take off to this side. So when you're looking at the graphs, you can see that mirror or that reflection. The line of reflection on these inverses is going to be that line y is equal to x. Okay, so let's take a look at this one. Checkpoint number 6 has us sketching f of x equals log base 9 of x. Now we went through in class how to key this into your calculator. When you go to your y equals button, okay, and you're about to enter in this side here, you're going to first have to hit your math key and then arrow down to where it has something that looks sort of like log base. And then it's going to open it up to where you can type in that little 9 and then whatever your x value is going to be. And then when you hit graph, you're going to be able to get the picture. For me, without that, I'm looking currently at y is equal to log base 9 of x. Rewriting that in exponential form, I have x is equal to 9 to the y. Well, that's not a very difficult function to come up with values for. Since 9 has a power of y, I picked y values this time, just for ease of that. So if I put a -2 in for y, I'd have 9 to the -2, or 1 over 81. A -1 in is going to give me an x value of 1/9. A 0 in, of course, gives me a value of 1. Anything to the 0 power is 1. 9 to the first power, 9 to the second power, and I'm ready to graph. Okay, so right about here, here, 1, 0, 9, 1, and then we fall off. So we're hugging the y-axis and then heading off to the right. When we look at these functions, we're going to be also finding that they're going to use the same transformations and the same way of transforming these functions as we did back in chapters 2. So you may need to look back at chapter 2.5 or even at our parent functions that were in chapter 2. Mostly 2.5 just to review the simple transformations themselves if you have forgotten how some of that works. So if we're looking at this one, okay, there is a shift put onto this function. We have a log base 3 of x main function and then a minus 1. Most of you are probably more comfortable looking at it like this. Now if you recall, a minus 1 at the back end, that is our down 1 shift. Okay, so first of all, let's figure out what our log base 3 of x function looks like. So if we have the function y is equal to log base 3 of x, we have x equal 3 to the y power. Okay, so the first thing I do, I come up with, again, a table of values. My y is a power, so I'm going to put those in rather than try to figure out x powers and then solving for y. So I'm kind of sticking to these values here. And I end up with 1/9, 1/3, a 1. Again, 0 power of anything is 1, and 3, and 9. Okay, so if these are my initial y values of this function, a down 1 shift is going to just lower them by 1. Okay, so the points I want to plot are going to be down 1, down 1, down 1, down 1, down 1. From what they, whoops, I was looking at the wrong number. I was looking at the x numbers. Come back to that far, because okay till then. How about that, and minus the, whoops, sorry. I don't know why I'm having such a hard time subtracting 1 here. Okay, now I can graph. So at 1/9 I want -3. Close to that. And -2 at 1/3, so in just a little bit. 1 is -1, 3, 0, and 9, 1. And there's my curve. Okay. Now, natural logs, we talked about them today. Our natural log is going to be the ln key on your calculator, and our base for those natural logs are e. So you're not going to see a's anymore. You're not going to see random numbers. We're going to be using e as that base throughout natural logs. So f of x is equal to log base e of x, which is the same thing as ln of x. Okay, so when a is equal to e, we just transform it into the natural log. It follows then that y is equal to ln of x, and x equals e to the y mean the same thing. Okay, so that's the same transformation as that we had with our regular log function. Okay, it's maybe easier to see, and we talked about this. If you show yourself that base of e, I don't know, it helps me anyway. If you're evaluating natural logs, again, you're going to be using the ln key on your calculator. So on page 377, again, we did a few of these in class. If you didn't get through all of them, maybe you want to punch a couple more in and just practice it a tad bit more. I guess that's about all I have to say about that one. We sort of went over it already. So let's just do a couple last practice. The checkpoints at the bottom, I just pulled A and C off of there. So if I do ln of 0.01 and hit enter, I end up getting this. So you give it a try. Make sure you see the same value coming out on your calculator. Even with a little bit fancier one like C had with a root x plus 2 to plug in, again, use your square root key, or not root of x, root of 3. Use your square root key, load it in like you always would, hit enter, and see if you get this. If you have trouble getting these values, or you're not quite sure how to do these still, make sure that we have a conversation about them. When you get questions that are a little bit easy like this, just simply using a calculator button, we don't want to miss them. All right, so here's the property table. This property table for our natural logs is on page 378. Notice it's almost identical to that other property table. Okay, so we still have inverse properties. We still have the one-to-one property in line 4. The natural log of 1 is still 0. Um, natural log of e is equal to 1. Okay, and again, by transforming them into exponential form, you can prove it to yourself without memorizing. So let's do that a little bit here. In that first one, I have ln of e to the 1/3. So currently, I have it in log form. So in this problem, we've got y equals log base e of e to the 1/3. So my x position is that stuff. All right, so x is equal to a, which in our natural log cases is going to be an e, to the y power. There's your one-to-one. For this first, that's a very strange looking one, 1/3 is equal to y. Okay, on letter B, we have the natural log of 1, and that is found on our table of properties. Okay, the natural log of 1, if I could back it up here, the natural log of 1 is 0. So if you've got it memorized, that's all fine and dandy. If you don't, though, look and find the value for yourself. So if you have y is equal to the natural log of 1, rewrite it. 1 is equal to e to the y power. The power of 0 is the only way to get a 1. So the value of that function, natural log of 1, must be a 0. So now put that in along with your 5, and we get an end answer of 0 for that particular problem. Okay, natural log of e in this one. Again, that can be found on our property table. The natural log of e is equal to 1. But again, if you don't have that memorized, prove it to yourself. Y is equal to natural log of e. I insert that. X is equal to a to the y power. The left-hand side, a plain e, you guys know that a plain number has a power of 1 always. Now your one-to-one tells you that y is 1. So you've just proven it. Okay, we could get it off the properties table that the ln of e is equal to 1, or you can do the rewriting and you can find the 1 yourself. So now I come back and use it. So 3/4 times that value, I get an answer of 3/4. All right, letter D. D is not starting out in log form, it's starting out in exponential form. So technically I'm looking at x is equal to e to the ln of 7 power. So if I'm going to rewrite this, I want it y is equal to the natural log of e, or of x. So that power gets written first. So y is equal to, and then I have on this side, I want my log information, ln of a, which of course for natural log is an e, and then my x. Okay, inserting that, because it is, I have a one-to-one going on. I have natural log of 7 is equal to the natural log of x. So 7 must equal x. One-to-one property. All right, checkpoint number 10. This was about as far as we had gotten in class so far. So finding the domain of f of x equals the natural log of x plus 3. Now in functions, okay, functions are only defined for positive values. Remember when we used our calculator and we were playing with our log buttons? If you put in a negative number, you got an error. Okay, so I need that value in my parenthesis to be positive. So my domain then is going to be just the values for which that occurs. So I need that chunk to be greater than 0. Okay, so solving, all the x values that I use need to be greater than -3. So stating your domain, it can start not on it, but just over -3. Okay, x is greater than -3, not exactly -3. Soft parenthesis, remember, does that. And it continue on through infinity. Okay, so those are the x values that could work in this function. All right, checkpoint number 11 is an application problem. So take a look at it there on page 379. It gives us a function. F of t is equal to 75 minus 6 natural log of t plus 1. Um, the t in there is months, which work in this, it was a human memory model, and it was talking about what the scores would be for exams or something based on time. So all it's having us do is practice using one of these log functions and seeing if we can evaluate it correctly. So let's give it a try. If we're on checkpoint number 11, part A, given 1 month of time, plug it into your function. So I'm looking at 75 minus 6, and the natural log, pen's going a little crazy again today, of 2. All right, so natural log of 2 has to be calculated first. So if you do ln of 2, I'm going to put roughly what my display screen gives me here. ln of 2 was about 0.6931471,806. Don't round any of it off until you absolutely positively have to. Okay, so I can do my multiplication by 6 yet while that value is still displayed on my calculator. I'll lose nothing. So timesing by my 6, now I'm looking at this. So to subtract that, now I just punched in 75 minus, and while I could still see it on the screen, I just retyped it, and I ended up with roughly 70.84 would be that person's score after a month. Okay, I do have problems that I want you to do and turn in. It's very essential that you practice with these problems. So I have, I don't know, it was 11 or 12 up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, about 11 of them or so. A lot of them have sets of 4 or 6 to practice with. This is just one out of there. Please do lots of them. So have these ready to go for me, and we can take questions and do more of them when we get to class.